In this video, we'll cover storage devices. First, let's look at the memory hierarchy. You might be familiar with this diagram. This indicates the latency, capacity, and cost of different types of memory, starting from static RAM and registers all the way to remote secondary storage. So, memory that is on CPU, typically registers and processor cache, they are the fastest type of memory, but they also have the least amount of capacity and are the most expensive. Then we have DRAM, where the latency of access for this type of memory is increased by an order of magnitude, but the capacity is much bigger. It is not uncommon to see personal computers with at least 4 to 8 gigs of memory and servers with up to a terabyte or more of memory. The cost is also significantly cheaper compared to static RAM, where it's about $10 per gigabyte. Then we have solid state drives. Now, these are disks that are based on NAND flash technology. Again, their latency will be slightly higher than DRAM, but their capacity is much higher, and you can typically get solid state drives ranging from 64 gigabytes to 1 terabyte in a single package. Their cost is also about $2 per gigabyte. Magnetic hard drives are among the cheapest online storage systems, but they suffer from much higher access latencies of in the order of milliseconds. Their capacities are much higher though. You can find hard disks of at least 1 terabyte or more. 6 terabytes are not uncommon these days, and they are much cheaper than all other online storage technologies. Their cost virtually 4 cents or less per gigabyte. All other types of storage we can sort of consider to be remote. They could be online or offline. So tapes, CD-ROMs, for example, anything that's on a library or is a removable media can be considered to be remote secondary storage, as well as remote file systems and web servers. Now, these have access latencies that are much higher than 100 milliseconds, but their capacity can be virtually infinite, and their cost is, compared to all of the other technologies we're looking at, they're virtually free. Now, another aspect that's very important to remember in this hierarchy is that registers, processor cache, and main memory, all of these technologies that rely on either on-die, SRAM, or DRAM, they're all volatile storage technologies. So as soon as the power goes off, or if there is some sort of crash, they tend to lose the information that is stored in them, and the others are more or less persistent. So let's quickly go through some of the basic storage classifications. I already mentioned volatility or persistency and durability. Now, this indicates the reliability of data storage. Volatile systems such as SRAM and DRAM can lose data as soon as power is lost. Then another classification is online versus offline storage. Online storage is always on and retrievable, tends to have maximum amount of performance. Offline storage systems may require external storage media that's not always connected, but it's an ideal choice for archival and data recovery. Whenever you just want to archive your data for, disaster recovery purposes, or if you just want to keep a copy of data in case you need to recover, and time is not necessarily of the essence, then offline storage is a good option. So let's look at some of the persistent disk technologies that we will be covering. First, we have magnetic disks, and these are nothing but platters of ferromagnetic disks with spinning heads that can read and write data. Now, we have a cross-section view of a disk, which consists of multiple disk platters, and we have heads that spin on platters. These heads are on both the top and bottom of each platter, so that's a surface. Now, the disk itself is divided into concentric tracks, and each track is divided into individual sectors, and essentially data is located using this paradigm of track sector. All of this translation is typically done by the on-disk firmware. As we just mentioned, magnetic disks tend to be the cheapest and densest online storage systems. The access latency for magnetic disks is typically in milliseconds, and this includes a seek time, for the time taken for the head to move from one track to another, the rotational latency, the time taken for the platter to rotate to get to the correct sector, and then the transfer time, the time taken to read the data off of the surface and transmit it through the bus to the computer. Of the three times, seek, rotational, transfer, seek and rotational time tend to be very high, especially for instances where the heads need to move across the disk multiple times. So magnetic disks are particularly bad for what we call random read-write performance. They're fairly decent for sequential read-write performance, but if there is a program that's randomly reading or jumping across multiple pointers on disk, such as disk records that are farther apart, then that type of access latency for magnetic disks is quite bad. Magnetic disks also have reliability concerns. Of all of the storage mechanisms that we've seen, disks are the online storage mechanism that contains moving parts. So they have a relatively higher failure rate compared to many of the other storage technologies. And you can imagine that in large data centers that employ, hundreds of thousands of magnetic disks, it's not uncommon for them to have to replace disks, almost every day. In fact, they'd have to replace even hundreds of disks because of their failure rate being amplified by the sheer number of disks that they use in the data center. Next, we have solid state drives. Now, these are drives that are based on NAND flash technology. So the actual flash cells, they are arranged as pages and then arranged as blocks. And all of those blocks are available to the solid state drive through something called the flash translation layer, or FTL. So this is a part of the disk firmware that maps individual disk I/O requests for a particular file block into an actual flash memory block and page. Solid state drives compared to magnetic disks are much faster. They're in the nanosecond range, hundreds of nanoseconds for sequential access. But they have a few interesting quirks. Now, it's easy to read memory off of NAND flash, but writing memory on NAND flash requires an erase. And sometimes you cannot erase just a single bit or byte. You may have to erase an entire page, even if it is to simply write a single bit or byte. Now, this is known as write amplification. And this also affects random write performance, because if you're writing randomly across blocks and pages in an SSD, then you sort of amplify the amount of space that you need to write. Another thing that I would like to mention about SSDs is they wear out compared to magnetic disks. And they have a limited number of writes, usually in a couple of million or billion writes per page. So there are advanced algorithms in the FTL to make sure that writes are spread out across all of the pages and blocks on flash memory. Solid state drives are definitely more expensive than magnetic and tend to have lower density than magnetic disks. And there are different grades of solid state drives. So the flash memory used on it dictates sort of the performance as well as the price. Now, the most expensive tends to be SLC. They're much less dense than the other solid state drive technologies, but they're also quite fast and consume a lot less power. In comparison, MLC and TLC are much more denser, but they suffer from slower performance and also tend to consume higher power than SLC based NAND flash. And finally, we'll talk about DRAM as storage. And of late, DRAM prices have been dropping quite significantly per gigabyte. And DRAM is quite fast for transactional systems. In fact, most databases tend to keep their working set cached in memory just to be able to improve transactional performance. DRAM also has the issue, as we discussed, of being non-volatile or non-durable. So there is a trend to using DRAM as a caching or first tier in-memory storage system. And one of the figures that you're seeing now is of Memcached, which is an in-memory cache, distributed cache system that can be used, deployed in a cluster. And this can be used to sort of speed up common queries or things that can get cached in the Memcache layer. So applications can pick up information quite fast through a Memcached cluster that's attached to a backend database.